Okay, now here's the one good thing about the next two sections. The next two sections focus specifically on patterns that work the same way. So, like what you were working on yesterday, you saw like the two questions we went over with Austin. It was going up by 5 each time, we were adding 5, we were multiplying by 2 each time, or in the warm up, we had a numerator and we had a denominator. Remember, yesterday I gave you a formula that had a factorial in it, and then even on the homework, there was like a cube one and cubed. All different kinds of number sequences and patterns were up fair game. Today we're going to focus specifically on sequences that work as you're adding or subtracting the same thing every time. And we have a special name for that. Although it looks like arithmetic, this is an adjective to the word sequence, describes the sequence, and we say arithmetic. So if you say arithmetic sequence, I'll giggle a little. It's arithmetic. So we changed the way we say it. Okay, and then tomorrow we're going to do geometric sequences, which also have a special characteristic. Okay. All right, so here's what you need to know about arithmetic sequences. The difference between consecutive terms is constant. Basically, in my own words, is I'm adding or subtracting the same thing every time. That's a pretty easy pattern for you to spot. You probably saw some of those on the homework last night. We actually saw it in the warm-up. Remember, Morgan told us the numerator was decreasing by 1 each time. The denominator was increasing by 1 each time. So we were adding and subtracting the same thing every time to the numerator and denominator. So that's pretty easy to spot. We call that thing that we're adding or subtracting a common difference. So we have a name for it, common difference. We label it D. There will be times when I might ask you, like, is this sequence arithmetic? If so, what is the common difference? So then you should know what that means. Here's an example, 1, 5, 9, 13. This is arithmetic Y. 1, 5, 9, 13. You're going up by 4s each time. So if you can recognize some plus or minus, and it has to be consistent for all the terms presented to you, then we can say it's arithmetic. Okay, remember tomorrow we'll add to the list geometric, so we'll be able to say arithmetic, geometric, or neither. And then we can say that D is 4. Now think back to our conversation in the warm-up, what Lexi presented to us. If we add 4 a whole bunch of times, what's that going to look like in our rule? 4n, n times 4, right? Repeated addition is multiplication. So that's going to be a sub n equals 4n. Okay, we'll know to start. Anytime it's arithmetic, you can start with that number, that common difference times n. And then I call it tweaking your equation. Okay, so if I check like a sub 1, that would just be 4 times 1, which would give me 4. Is that actually the first term over here? No, how do you get from 4 down to 1? Minus 3. So if we add in the minus 3, let's put that in our rule for n minus 3. And maybe just double check another one if you're not sure. So I'll pick a sub 4. A sub 4 equals 4 times 4 minus 3. That'd be 16 minus 3 or 13. Is our rule working? Okay. Excellent. Okay. Now, we had this conversation yesterday because we saw a function, or we saw sequences like this. What type of function is that? Linear. Okay, so this is a side note. Arithmetic sequences look like linear functions. side note, arithmetic sequences are always going to look like linear functions. Because you're always going to say, oh, I'm adding that thing times n, and then I tweak it, plus or minus some number. That's what Lexi did in the warm-up. Okay, she said, oh, I'm subtracting 1 every time, negative 1n. Add or subtract whatever she needed to get the actual term. So you could tell yourself, like, think something like mx plus b, because that's linear, right? Slope times x plus b. B is like your tweak what that number is, okay? And m is your d, it's your common difference. So whatever you're saying you're adding or subtracting every time, that is your slope. So your common difference is your slope, is what I'm trying to say. Okay, I want to point one more thing out because I'm going to give you some rules and things, but I also want you to just be like thinking about patterns and sequences, right? Because you don't have to follow a formula. You can still generate these rules. Remember when we wrote for n and we were trying to figure out what number got here? So we were looking at a sub 1 and we must have subtracted 3. Let's look up here at this sequence. 1, 5, 9, 13. We were adding 4 every time. If there was a term before a sub 1, what would it have been? Three? Negative 3. It would have been a negative 3. So that negative 3 plus 4 would get us to 1. 1 plus 4 got us to 5. 5 plus 9 got us to 13, so on and so on. That negative 3, that term before the first term, we saw that in Lexi's. Okay, that's the number that goes in the back. Okay, so it's like the thing that would have come before the sequence. If you can figure out what that is, then that's also the number you should be adding or subtracting. Okay, so I like to do it this way. It's very much pattern-based. Here is a formula from the book. So if you are like a formula, a rule person through and through, you love algebra, you love substitution, you love solving, go ahead, write the formula down. If you want to see a problem worked out with this formula because you are a formula-loving person and you don't want to think outside the box about a pattern, then you can look at that example in the textbook where they write a sequence with this formula. I like this formula. It's fine. I know this formula very well. I just don't love it in sequences and series for people who are learning about patterns because it takes all the fun out of finding the pattern. It's just like plug and chug and solve, and then you're like, forget about all the beautiful parts about the sequence. Okay. So this would be the first term. You have to know the first term. Okay. This would be your nth term. And then this is n minus 1 quantity times d. But I'm going to give you an or. Because if I have my choice and I really wanted a formula or a rule, this is also a rule I really like. Because remember I said arithmetic sequences were really linear, where d was equal to your m. Okay. So your mx gets replaced with dn, because your input is n, your slope is d. And then remember how we said like what would have come before that first term? I could say plus a sub 0. Now, we will kind of go under the assumption that the first thing listed in a sequence is really the first term, unless we're told like that it's a different term. So then I'll always just be like, well, can I see based on the pattern what would have been the thing before it? What would have been my 0 term? That was that negative 3 we saw in the first example. So that's like your y-intercept, essentially. Side note, these two formulas are exactly the same. If I distributed this d I would get a sub n equals a sub 1 plus dn minus d. Doing a little bit of arrangement, a sub n is equal to dn plus, I'm going to protect it with parentheses, a sub 1 minus d. And if you take the first term and you subtract the common difference, like we did in that example, you're getting the a sub 0 term. Okay. So this is a sub n equals dn plus a sub 0. But I like the linear one better. Makes so much sense to me that it should be a line. Okay, you probably don't even have to write these down. I just want you to have like a little conversation. Let's get out of our heads for a minute here with formulas. Are these two sequences arithmetic? Yes, no, argue with your group, why or why not. Go for it. Sorry, someone moved my magnet.
That would be n.
Yes.
6 n. Six n minus 5.
Well, the first one would, if it starts at 5. 6n, 6 times 1 is 6 minus 1 is 1. It's just the 0 that we're going.
I will let you. This I would call this. Okay, what did you say for the first one? Arithmetic? No. It looks like it could be, but then the difference changes, right? So for whatever terms you're given, you would check. Like, does it continue forever? Okay, it should be true for all. But we go +4, +4, and then as soon as you find one that doesn't match up, that's a no. Okay. What about the second one? Arithmetic? Yes. Okay. What's the rule? A sub n equals 6n, because your common difference is 6, so that's your slope. You're going up by 6. And tweak it. You get your first term? -1. Or you could think about it if it was +6 for everything, what came before 5? 5 minus 6 is -1. That's the number that goes in the back. Okay. You guys, write a rule for this sequence. And then find a 20th term. Go for it. Write a rule and find a 20th term. Are you okay? Okay, will you try to write a rule for this sequence?
15. 15. 15n plus 2. I mean, not 15n plus 2. 15n plus 17. That's what I meant. I confused myself.
Are you taking your turn?
Yep. 13 plus 17. Thank you.
Okay, what's your common difference? What are you adding?
15.
15 every time. So that means that D is equal to 15. You may or may not have to write that down. But that helps you. Then for the rule, you can start A sub n equals 15n. If you are adding or subtracting the same thing every time, find the D, find the common difference. It becomes repeated addition. That is multiplication. D times n. That's like slope times x. And is this okay for your final rule? No, because it won't generate the actual numbers in the sequence, so how we tweak it? Plus 17. So you might be thinking about a sub 1 equals 15 times 1, which is just 15. So what's 32 minus 15? Well, I would need to add a 17 to it. Or you can do 32 minus 15, 22, 17. There we go. That's the number that goes to the back. So what's a sub 20? What'd you say? 317. You know how they got that? Sub 20 in for n. 15 times 20 is 300 plus 17 is 317. So now we can quick get any term we want in the sequence. Okay, one last example. You guys are doing a great job. You're almost there. What if I don't just give you like a list of terms in the sequence? What if I give you just like 2 terms in the sequence and they're not necessarily right next to each other? Okay, so I want you to kind of jot down in your notebooks. I've got a sub 5 equals 10. So that means which term is 10? The 5th term in the sequence is 10. And then I'm telling you a sub 30 equals 110. So the 30th term in the sequence, way far out, is 110. We want to get a rule for the nth term. Have a conversation with your groups whether you actually get to the full rule or not. But start like conversing like what good is it if I just have 2 random terms of the sequence? Talk to each other. Talk to each other. Problem solve. You guys are really good at patterns and ideas. Okay, talk to each other.
Wait. Yeah. Yeah, it is.
How? 20.
4 times n is 20 minus 10 is 10.
So 4 times n, so that would n would be 5. So 4 times 5, 20. That's 10. 4 times 30. How did you do that?
I'm so smart. I just randomly did something and I found I just like took numbers between them.
I don't know. Draw squares.
What are you doing to my
Change
pepper?
from stars and drawing squares. That's what I was trying to
Do
do.
your
But
best.
apparently I can't.
They're vandalizing my paper. I really just fixed this. I have the
How did you do this?
I got it.
Because squares are better than stars.
Yeah, you're right. Squares.
No.
Okay, also, explain competitors.
No, that's vandalizing.
So n equals 5. And a sub n is 10.
Do we have to use formulas or anything?
Do we have some ideas we can at least share out?
Plus something.
Kyle, you got an idea for us?
Yeah,
Okay. Whatever you want to tell us, we're listening.
for like the actual sequence.
If you want to give us your rule, sure.
I got 10 and minus 40.
Minus 40.
No. Oh, minus 40. Oh, that's right. That was 4.
So I might check a sub 5 equals 10 times 5 minus 40. Works? 50 minus 40? Yeah. A sub 30 equals 10 times 30 minus 40. Shoot. That's That's gonna be 300 minus 40, so that's gonna be a 260. Okay, so this is a very common thing. You'll write a rule and you'll be like, yeah, it works for one, but you might want to check it for another one, because if it works for two, I'm pretty good. I'm feeling like this is probably it. Okay, so what else could we share out? Zach, you want to say?
We had 4n minus
4n minus 10. You mad at me?
No.
Did you have the same answer?
Yeah.
10. Do this.
Okay, so maybe Austin could tell us where one part of that comes from.
I just like randomly did something. I did 30 minus 5, which is 25.
Okay, wait. Let's stop and think about that, because I've heard different things around the groups. And think about your group. Did your group ever do 30 minus 5?
Okay.
Some groups? Okay, what does that 25 represent?
The in between.
The number of terms, like, in between those two, right? So, like, this is, you have, like, a sub 1, which we don't know, a sub 2, a sub 3, a sub 4. Here's a sub 5 is 10. And then we have, like, a sub 6, a sub 7, dot, dot, dot. And then, like, here's a sub 29. And then all of a sudden we know a sub 30 is 110. There's a whole bunch of terms in between. So what it's saying is there's 25 terms in between. Okay, good. What else did
And
you
then
do?
I did 110 minus 10, which is 100.
Okay, and then 110 minus 10. So stop and think. Did your group ever do 110 minus 10? What are you finding when you do 110 minus 10? Other than the number 100. What does that represent?
The answer is in between.
The numbers in between the numbers. Like the change, like how much you totally added to 10 to get the next term in the sequence, which is not really the one right next to it, but 25 down. Okay, so 100 between terms, okay, or how much we like added from one term to get the next. And then if you think about that, you went from 10 to 110, you added 100, but how many times did you add in between? Individually. How many times did you add? 25 times you added something, right? Because there were 25 terms in between. We went plus something, plus something, plus something, plus something. 25 times. So on this one, I would argue to calculate D, Austin's telling us to take our 100 divided by 25 and get 4. D was really 110 minus 10 over 30 minus 5. Does this formula look familiar? Related to linear functions? What did you just calculate right there? Slope. Isn't D supposed to be your slope of your line? And you knew the y value, like the term, and then you knew what numbered term it was. So you did the difference in the terms over the difference of how many times you added something. Okay, so you can think about it like slope. There's different ways to think about that. And then, okay, does any other group, can you describe to us how you got the minus 10? Did any other groups have that? Did you guys get there to the minus 10?
Yeah.
Okay, tell us how you would, because Zach gave us 4 and minus 10. Austin gave us 4. How did you guys decide on like minus 10?
We did 4 times like 5 because it's 5, and then that was 20. And then to get to 10.
Okay, normally we're often like checking that first term or we're subtracting from the first term, but you guys are using a sub 5 equals 10. So you're saying we know a sub 5 equals 4 times 5 because we just found the difference to be 4. So that would be a sub 5 equals 20, but it's only supposed to be 10, so I'll subtract 10. And that becomes part of my rule. Now, we should be wise, and like we did for Kyle's rule, we should check the second one, right? Does it work when you put 30 in for n? 4 times 30 is 120. 120 minus 10 is 110. Does it work? So we'll use that one. If you're a very I want to step by step, I want a set of rules every time I see that problem, what I would say is calculate d as slope, plug in to the formula as slope, and then, tweak. But I also like that you guys were just thinking about it. There was a difference in 25 terms, and then I added a full 100, but I did that 25 times, so then my difference is 4. That makes the sequence more like a pattern to you, okay? Hopefully then you'll be able to do that on your own someday. Okay, your homework assignment is in page 422. Everything on the homework, unless it comes from a little review section, should really be arithmetic. So instead of yesterday how you had to think about all different kinds of ways numbers could be related, just looking for patterns, you should see, if I'm asking you to write a rule, you should see that you're adding or subtracting the same thing every time.